All right, everybody. This is the solution video for 415, April 15th. This one's going to run a little long because I'm going to run through quiz 8 and then I'm going to go back over that homework that I wanted to do a solution for last time that I didn't get to. All righty, so that's all right. Kind of wish I had more room, but it doesn't seem like it's going to happen tonight. Okay. Yeah. Okay. So for this first one here, so we got, I guess the key here is to figure out what your time tick is, right? What is 1 unit of time in this case? And I have had seen people in the past use minutes as their time tick. I would say that would needlessly complicate things. So let's go for T is number of class periods. All right, so if T is the number of class periods, then it simplifies things a little bit. So we have a decrease of 5%. So that means A is going to be 1 minus 0.05, 5 100ths. And so we have an A of 0.95. And this is the decay factor per class period. Okay, and so now the question is, when will your IQ be below 60? Well, the easiest way to find this is, well, so we know that it's a decreasing exponential, and we know that decreasing exponentials look like this guy, right? So there's never a time where it comes back up, right? This doesn't happen with exponential equations, right? We don't go down and come back up. We don't go down and turn around. So that means that if we find the point where it's 60, any t greater than that, any number of class periods you spend greater than that number we find, will be less than 60. So find the t that makes it 60 and then say t has to be greater than that. So find t at 60 and any time greater will work. All right, so how do we do that? Well, we start out with a C of 150. So we got C equals 150. A equals 0.95. And so we just want to solve our cat, our 150 times 0.95 to the t for when this thing equals 60. And so divide by 150, right? Divide both sides by 150. And that simplifies to 2/5. All right, that's 20 times 3, that's 50 times 3, that's 2/5. Okay, well that means that I have, when I do my log trick, I'm going to have t times, I'll just do regular log. Log of 0.95 is equal to log of 2/5. And that means that t is going to be log of 2/5 divided by log of 0.95. And so that's the pattern you see when you're solving these exponentials every darn time. And if we carry that out, we look at the right sheet of paper when we carry that out. It looks like about 17.8639 class periods. So we say t must be greater than that. All right, so that's about that. All right, so linear function, finding a linear function. So we got two parameters, right? I have m and I have b. And I need a y equals mx plus b. So I got two things to solve for, and I've got two combinations of x and y to solve them with. So here we go. I'll use my slope formula. And so I'm going to take this, right? I'm going to take my lowest x and call that x1, and take my higher x and call that x2. And so that's where I'm getting these numbers from. So I'm going to plug that in. 5 minus 18, 8 minus 3. And we get negative 13 fifths. Man, I could have done a better job picking that number, couldn't I have? Oh well, it's just a number, right? And yeah, okay, so I could solve through substitution, right? I could say, okay, there's my slope. I'll pick 1 point and solve for b. But I'm going to encourage people, again, to use point slope form. Y minus y1 is m times x minus x1. All right, and I'm going to use the x1s. I don't have to. I could use x2, y2 here. That would be totally valid, but I'm just in the habit of using my lowest x, so I'm going to do that. Y minus 18 is negative 13 fifths x minus 3. And so we'll clean it up a little bit. So I'm going to distribute this. I'm going to get, go all the way up here. Y minus 18 equals negative 13 fifths x minus, and that'll be 39 fifths there. So I'm doing the 13 times 3 there. And so I end up with y equals, oh, I'm sorry, that would be a plus there, plus negative 13 times negative 3, excuse me. So I get negative 13 fifths plus 39 fifths plus 18. And I know y'all like decimal places, but I don't. And, you know, that's okay. And it's okay to like decimal places. You know, that's fine too. But I'd rather multiply this 18 by 1. So I'm going to multiply this 18 by a flavor of 1 called 5 divided by 5. And if I do that, what I get here is negative 13 fifths of x plus 39 fifths plus, do 18 times 5 real quick, 90 fifths, right? So I multiplied the 18 times the 5 and then kept the fifth on the bottom. And yeah, comes out to y equals negative 13 fifths x plus, what is that, 129 fifths? And that's a number just as good as any decimal number you can come up with. It means the same thing. It weighs the same in your hand. So I'm happy with that answer. And I would like to point out here that what we have here is this is negative mx1 plus y1. And that is b all the time, every time. So if you have that formula, you can definitely use it. That equals b. All right. Now, oh crap. I'm in exponential, guys. I said linear up here. I made a mistake. I must have meant exponential. All right. So we've done many examples of these, so I'm going to run through this a little bit quick. So we always got a cat. And we got two solutions for our cat in this case. I've got that CA to the third is 18, and CA to the fifth, or excuse me, to the eighth equals 5. So I'm going to divide those suckers. I don't see any reason why not. All right, that gets me 18 to the 3 minus 8, or A to the 3 minus 8, excuse me, is the same thing as 18 divided by 5. So these two things are equal and these two things are equal. So if I take their ratios, they're also equal. All right, so I get a to the minus fifth is 18 fifths. And then I flip it, right? I take the thing, so I solve this in my head. I say negative fifth times something equals 1. I want a to the first power there. And what that something is negative 1/5. All right, so I just take that. A to the minus fifth times negative 1/5. Well, that's definitely a to the 1. And if I do it to one side, I got to do it to the other side. So that's 18 fifths to the negative 1/5. And that's going to be 0.774. All right, so now I come back to this guy. I say, all right, I know a now. So c is the same thing as 18 over a cubed. Well, that's the same thing as 18 divided by 18 fifths to the negative 1/5 cubed. So when I'm going in my calculator, I just cube this thing that I just found here. I just go ahead and cube it, answer cubed, then 18 divided by answer, right? And if we do that stuff, I get 38.3, or no, 8.2. All right, that looks pretty ugly. 8.2. All right, so there's your one more of those. Yeah, there it is. Oh, solve the following. Da-da-da-dum. All right, so I'm going to put a up here because a takes a minute. So a. So first thing I'm going to do is step 1, I'm going to do that division rule. So that gets me that log of x cubed. And this is not the only way to do this, guys. There are other ways to do this. Log of x squared. E. X to the e. There we go. Sorry, guys. It's getting late for me here. Log of x squared is 9. All right. Then I can pull everything out, right? 3 logs of x minus e logs of x minus 2 logs of x is all equal to 9. And so now I see I have a common factor. So I'm going to factor it out. Log of x is times 3 minus e minus 2. And that's equal to 9. So I have that log of x is 1 minus e, and that's equal to 9. So I'm solving for this right now, so I'll just divide both sides by 1 minus e. All right, so log x is 9, 1 minus over 1 minus, whoops, over 1 minus e. So then x, I use my exponentiate. X is equal to 10 to the 9 divided by 1 minus e. And you can compute that if you want, but that's a pretty answer to me. That's an exact answer to me. And if you gave me a decimal number, it'd mean the same thing to me. So I don't see any reason to keep going. So let's see. The only other trick here is I did, so step 2 was p log rule, right? And then step 3 was exponentiate. And then you were done. All right. This guy, so there's another way to do that. Instead of doing this, where I expanded, I could have contracted first. So I'm going to investigate that one too. So, well, it's a video, so y'all can go back and look at this part. I'm going to give myself more room here and just start over and do it through contraction. So method 1 was by expansion and factoring. method method 2, we're going to use by contraction and exponent rules. And that looks like, okay, so I got this guy, right? That's a divide rule because it's minus. So what I have is I have log of x cubed over x to the e, and I'm going to divide by x squared, which is the same thing as multiplying by the reciprocal of x squared. And that's going to be equal to 9. Now I look here and I say to myself, well, I got x squared over x, or x cubed, so I'm left with x to the first power right there, right? So now I have log x over x to the e. Now this is another exponent rule, right? I got x to the 1 divided by x to the e, so we know that's going to be log x to the 1 minus e is equal to 9. Now, I can exponentiate if I wanted. Now I'm going to plug rule. 1 minus e log of x is 9. Log x is 9 over 1 minus e. X is 10 to the 9 over 1 minus e. So same darn place, maybe a few less steps, and you can do it by expansion or contraction. So that's it's a good idea, right? No matter which way you started, you could have gotten to the answer. So this is one of those be like Young MC and move something kind of things, right? Either way you moved, whether you expanded first or contracted first, you were going to get to the answer. All right. Number B. B is pretty easy here. So first thing you do, exponentiate. You can use the product add rule if you want, but it doesn't get you any closer to the answer. If this was log base 10, it might be a good idea, but yeah, not so good here. All right, so we'll exponentiate, right? 10 squared x, that's what I get on that side when I exponentiate, right? My log and my e base will cancel. And since my base is e, base e, I have to put e to the 5th power on that side. Doesn't work out so nice as it did when I did base, when we had a problem like this where this was base 10. Slightly different situation, but x is e to the 5th over 10 squared, and that's a number. So this, or the decimal version, I will be happy with. Yeah, so C now. C takes a little bit of work. So contract first. I'm going to do this by contraction. I don't think you could do it another way. So I'm going to use my subtract or division rule there. I'm going to say log of t minus, or over t minus 2 is equal to 3. Now exponentiate. T over t minus 2 is the same thing as 10 to the 3rd power. So no subscript on the log, so it's base 10, right? Okay, so now I'm going to multiply both sides by t minus 2. And that'll get me t is equal to 10 cubed times t minus 2. So distribute there. T equal to t times 10 to the 3rd, almost like scientific notation, right? Minus 2 times 10 to the 3rd, exactly like scientific notation. Okay, so now I got a constant here that's minus, and I got a smaller t than this one. So I want to subtract this over, or add this over. So plus 2 times 10 to the 3rd minus t. I get So I have 1,000 T's, and I'm going to take 1 away, so I better have 999 T's, right? So I have 2,000, right? 2 times 10 to the third equals 999 T's. And so then one more division later, I get T is equal to 2.002. All right, there we go. That's how that goes. Now this problem. Well, the math is right. So, but you will see that the answer gives us a ridiculous amount of time that you'd have to wait. So my guess is that they don't wait till you're down to normal background radiation levels. They send you home, you know, maybe 2 half-lives. So let's figure that out, right? So what do we need to find? We need to find the half-life, and we need to calculate how long it takes to get back to normal radiation levels. This is background radiation. Everything you touch is kind of that radioactive. All right. So let's do the half-life first, right? Here's my R. So my A is going to be 1 minus 0.1189, and that's going to be 0.8811. All right, don't need C's for half-life, right? I just know that there's a T I can put this A to that gets me 1/2. And if that's the case, then I use a natural log trick, and I have T is equal to natural log of 1/2 divided by natural log of A every time, right? So let's fill in the pieces. Natural log of 1/2 divided by natural log of 0.8811. And that gets me 5.476 hours. So 2 half-lives, you're down to 1/4 of the radiation you started with. Yeah, it's pretty safe, right? I don't know. I'm not a radiologist. So let's do the original problem, right? So you notice that every time you solve one of these things for T, you get log of the output value divided by log of A, right? Every time. So what do I want to know? I want to know when my output is 10,000. Log of output value divided by initial value. All right, so it's always CA to the T is, something. So it's always A to the T is, something divided by C. So it's always T is equal to something divided by C, log divided by log of A, every time. So I'm not even going to go into the details. I'm just going to say I started out with 50 megabecquerels. There it is. So I'm just going to say T is the natural log of 10,000 divided by 50 million divided by natural log of 0.8811 every time. And I don't know, maybe I'll just calculate that out. Natural log 10,000 divided by 50, 0.00000. All right, divide that by natural log of 0.8811. Yep. All right. So if you wanted to wait till you got back to normal background radiation, what do you think? Just take a guess. 8 half-lives? I don't know. Well, it turns out that it's 67.285 hours. That's a lot, right? How many half-lives is that? I'm going to divide that number by 5.476. That's 12 half-lives. Holy shit. All right. So that's how that one gets done. Hope that made some sense there. 12 half-lives. This is back to that caffeine dosage problem, right? I'm drinking coffee here at 8 o'clock at night. Maybe you can tell me when I can get to sleep. All right. So this is a extra homework. I assigned it, and myself and everyone else kind of forgot that it was due. So I had 2 people turn it in. So it's going to be extra credit. You're welcome to do it for extra credit if you like. It's got some good practice stuff on it. So carbon-14 decays into nitrogen. So this is the carbon that they use for carbon dating, right? And we can actually figure out here how long it takes, or how long ago you can use carbon dating to figure out where things are. And your next question is, well, how do we know how far or how old things are if carbon-14 has a half-life of, well, we'll find it out soon, won't we? And the answer is there's other things that you can use to do carbon or dating with. You don't have to use carbon-14. And there's other ways to get at it, right? You can observe the layers of rock. You can date when rocks were formed out of magma, and so on. So anyway, interesting geology stuff and paleontology, some of my favorite stuffs. But no worries, we'll keep doing math. Alrighty, get my notes on this one. Okay, so what do we want? We want the decay rate and the half-life. And find the decay rate. Well, to find the decay rate, wait, got it right here. Good, right? That was pretty easy to find it, right? Yeah, it's just sitting right over there. Now we do have to carefully convert it into a percentage, right? Because it's a percentage. I told you it's a percentage, and it looks like a decimal, right? Well, that just means it's just smaller when we write it as a decimal. Because what is this, right? Percentages is percent, right? Out of 100. It is incorrect that the Roman centurion commanded 100 troops, but it is correct that percent means per 100. So this is actually a fraction out of 100. 0.0121 hundredths is the same thing as 0.000121. So this is our R. So 1 minus 0.000121 is, where to put it? 0.999879. I apologize, folks. I'm getting a little silly here. Alrighty. So there's our growth factor, or our decay factor. And we need all those darn digits, right? If we're going to get accurate answers for this thing. Okay, so decay rate, check. Half-life. Well, hey, wait. Half-life is where I get half of what I started with. So the stuff divided by the initial value will always be 1/2. Oh, so in my formula where it's something over C divided by natural log of A, right, from that last page, well, now it's just T for half-life is natural log of 1/2 divided by natural log of A every time, right? So that's natural log of 1/2, natural log of 0.999879. And that is 5,728.14 years. So it takes about 5,000 or almost 6,000 years for there to be half of the carbon-14 in a sample that there was previously. All right, good to go. Now we got population of Delq, North Dakota, 10 years after it was founded. All right, find the founding population and the annual growth rate. Oh boy, how do I find the founding population? Oh wait, there it is. I found it. Sorry, I'm getting silly. I'm not trying to be a smartass here. And the annual growth rate. Okay, so 1.02 is the annual growth factor. So 1.02 minus 1 equals 0.02 is the annual growth rate. Done. Check. That's all I was looking for there, folks. This was a check on it, right? Like if you were on autopilot, you could get really far with this thing, you know, doing sort of the ritual of, you know, maybe this ritual where you, yay, for we divide the natural log of 1/2 by the natural log of a, or you know, the 1 minus a kind of thing, or something, or a is 1 plus r kind of thing, or something. But the idea here was I was kind of looking for a conceptual check. Do we know what each of these values means? And if you do, then this is a pretty simple problem. Okay, so this is an algebra game. The idea here is I claim, so here you might recognize something similar to a finance formula, maybe with 1 compounding per year. If you did, then I would say good job. But here we just want to kind of play with the algebra. So we have to start with one side and show that it's the same as the other side. So I'm going to start with the left-hand side. So if we start with the left-hand side, we can do something like this. We can say P plus PR, whoops. Left-hand side, P plus PR, and I'm going to take this R and I'm going to distribute. So I have PR plus PR squared, right? All right, now I got a P in everything. So why don't I factor it? Factor P. All right, so P. So if I factor a P, then I just got a 1 on that term, then plus R plus R plus R squared. Oh, so I have P 1 plus 2R plus R squared. Now, if you have practiced your algebra sufficiently, then you may have memorized this pattern, because this pattern is 1 plus R squared. And I'm not just going to say that. I'm going to say note that is 1 squared plus R again plus R squared is 1 plus 2R plus R squared. So I have shown that this is equal to P times 1 plus R squared. And wait, wasn't that the goal? So I can come up here and I can say something like, therefore, P plus PR plus P times 1, or sorry, not quite right. P plus PR plus P plus PR times R is indeed the same thing as P times 1 plus R squared. And, you know, finish it off. QED. quo ad demonstratum, I think. I'm not a Latin guy. Anyway, okay, one more. So this one, we're going to do this. So there's two ways to go about this, right? On the 236th day of the year, they had this growth rate. So what assumptions do we need to make here? Well, we need to assume rate is not fluctuating. What I mean by that is that we're going to go ahead and assume that the rate that they got for the first 236 days of the year, that's pretty consistent for the whole year. So I'm going to say T is days. So then if T is in days, then what I can say is that my growth factor to the 236th power, right, 236 days, is going to be 1 plus 1.0 plus 0.443, right? Because this would be my growth factor, in terms of 236 days, right? And block in periods of 236 days. That's my growth factor. Okay, so a to the 236th power is 1.443. So then a is the same thing as 1.443 to the 1 over 236. And you get about 1.00156. But I didn't want to know the daily growth factor. I wanted to know the yearly. Okay, well, there's 235 days in a year, right? 365 days in a year. Geez, I'm getting tired. All right. A. Well, I'm going to put A to the 365th power, right? And that's the same thing as putting 1.443 to the 1 over 236 to the 365th power. Ignore that 1 there. Okay. So 1.443 to the 365 divided by 236 should be my yearly growth factor. And that number is 1.76, which means that R is 0.76. Done. All right, I'm going to go back to 5. That's going to take a whole sheet of paper. So we're just going to do this one real quick. Now let's read it, right? Let's read it first. So what do we have here? Bottom of an ocean of air. How poetic. Each increase of 1 mile of altitude causes the pressure to drop by 20%. So it looks like miles is our input. And it's miles above sea level. And that's just for each increase of 1 mile of altitude, right? That seems pretty easy to go. And then we have air pressure at sea level. So it looks like that's our initial value. So I have a C is 14.7 psi. And I have an A is 1 minus 20%, or 0.2 is 0.8. So now it says, wait, find M of X, the air pressure at an altitude X miles above sea level. Well, geez, it looks like I just wanted the formula. I didn't even want a number. All right, so the only trick here is that I don't want M of T, right? I want m of x. Well, that's not too bad, right? I just put m where I'm used to, or I put x where I'm used to putting t. Wait, so I got a C, 14.7. I got an A, 0.8. And I'm using x instead of t. So I'm going to put an x up here. And we are done, chillins. That problem is done. All right, so let's look at this one. This one's going to take the biggest amount of time. So let's record our values, right? There are 65,000 words in this dictionary they're talking about. And we want to know how it is that Alan can guess the word that Kelsey is thinking of by asking at most 16 questions. Well, let's do it to it. Let's start. I don't want that. I want a blank page. Add page below. Plain paper. All right. So first of all, we got, it could be the first word. It could be the 65,000th word, right? And that's all Alan knows. Okay. Well, Alan's going to say, you know what? Say, you know, the middle of this is 32,500, 32,500, right? So he's going to say, is your word after the 32,500th word? And the answer is yes or no, right? The answer is yes. So we had 65,000 possibilities, right? So Kelsey says yes or no, right? Either way, we can throw out half of this number line, right? And I'm running out of pencil batteries, so I'm going to go a little bit quicker now. Okay, so I don't know. Say she picks the 40th word, just so we have somewhere to be, right? Okay, so she's going to say, Alan's going to ask, is your word greater than, or is your word after the 3,000 or 32,500th word? And Kelsey says yes, because she picked the 40th word, right? Okay, so now Alan has this number line to work with. First word, or 32, well, let's see here. Divided by 2. All right, so the midpoint's 16,250. All right. And Alan's going to say again, is your word over here or is it over here? And again, Kelsey says, no, it's less than that. So now, so we had 65,000 possibilities, then 32,500 possibilities. Now we have 16,250 possibilities. Okay. And the middle of that, 8,125 possibilities. All right. Is it greater than that or less than that? Well, it's the 40th word, so it's less than that, right? So now we're down to 8,000 possibilities. 125, that's the first. 81, 25. All right. Half of that's 4,062.5. So I'm going to say 4,062, right? Is it greater or less than that? Well, it has to be a whole word, so. And hers is the 40th, so she's still going to say less than. So now we got this many. worry about. And half of that, 4062 over 2, 2031. All right, it's less than that. $20.31 over 2. That's 10.15. Is it less than that? Sure is. $5.07 in the middle now, and you see we're cutting it down like crazy. 5.07 in the middle. It's less than that. So now I put 5.07 on the end. Divide by 2. I'm going to call this 254. It's 253.75, so I'm going to call it 254. Is it less than that? Yes. $254 over 2. All right, now the middle is 127. All right, is it less than 127? Yes. 127 over 2 gets me 63.5. I'm tunneling right in, right? 63.5. All right, so I say, is it greater than 63? No. Well, 127, 63, no. All right. Then it's got to be between 1, 63 over 2 is 31.5. Call it 31. All right. Less than 31? No, it's not less than 31. All right. So now, so all the way up to this point, I've been throwing away the top end, right? But now the answer is no, it's not less than 31. So now I throw this part away. So now I'm looking between 31 and 63. Well, how do I find the midpoint of that, y'all? Well, it's very simple. I'll take the average. And I get 47. So now I say, is your number the greater than the 47th? And the answer is no. So now I say, okay, it's in between 31 and 47. So what do I do to find the midpoint? I take the average. 31 plus 47 over 2. And that's 39. And so now I say, hey, is your number greater than 39? And Kelsey says, yes, in fact it is. All right, so now I have between 39 and 47 to worry about. Well, I take the average again. 39 plus 47. Divide that sucker by 2. Get 43. 43 is in the middle now. Is your number less than 43? Why, yes, it is. Okay, so now I have between 39 and 43. Take the average again. 39 plus a 43. Divide by 2. 41, right? And look here. So there's 39, 40, 41, 42, 43. That's it, right? 4 numbers, or 1, 2, 3, 4, 5 numbers left to choose from. Is your number greater than 41? And Kelsey says no. And I say, well, your number was greater than 39 and it was less than 41. It had better be 40. And so let's count back, right? Made 1 guess, 2 guesses, 3 guesses, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then 16, right? My final guess was, is it 40? And wait a minute. Let's see, I'm gonna use the log base on this calculator because I'm using a fancy TI-84 today. So I'm gonna go to math. And no, that's not gonna get it for me. I'm gonna go to second catalog, that's second 0. And then I'm gonna go alpha L. And that didn't work. So I'm gonna quit, go to second catalog, I'm gonna hit L. There it is. And I'm just looking for something called log base. Log base, there it is. I'm gonna say log base 2, right? Because I wanna know how many powers of 2 fit in here, because I'm halving my possibilities every time. I'm just gonna go, so what I'm doing here is I'm saying log base 2 of 65,000. And that is 15.988. About 16 guesses, huh? And that is the big secret on that one. And that's where we're going to leave it tonight. And I'll see you guys tomorrow.